So I'd like to look at a probability question that requires using the sampling distribution for the sample proportion. So here's the setting. Let's pretend 500 adults were asked the following question. Do you finish the milk that's at the bottom of the cereal bowl after you've eaten all the cereal? And let's pretend in our sample of 500 people, 0.67 or 67% of them said, yes, I do drink the milk that's left behind after I finished eating the cereal. Okay. That said, let's assume we know something else. Let's assume that the population proportion, in other words, the proportion of people in the whole population who finish the milk that's at the bottom of their cereal bowl is P equals 0.7. Okay. Quick comment here. When you know a fact about the population, we refer to that as a parameter. And then this p hat over here that was computed based on the sample 500 we refer to as a statistic. Now, in an ideal world, every time we calculate a p hat, it would be nice if we got the true population proportion. But there's always going to be some variability. We might have just picked 500 people such that these 500 people are less likely to finish the milk that's at the bottom of the cereal bowl. Okay, so let's start answering some questions based on this hypothetical question. So part A, let's find the mean and the standard deviation of p hat. Okay, so we have two formulas for that. The mean of the p hats would just be the same as the population proportion, which in this case would be 0.7. Okay, and then secondly, the standard deviation formula we have is the square root of p times 1 minus p over n, and that was proved in a different video. All right, so if we get this, we get 0.7 times 0.3 over 500, and we'll have to type that into our calculator. So let's just do that quickly. So 0.7 times 0.3 divided by 500. Yeah, we'll hit enter that. And then we want the square root of that answer, or to the 1/2 power. So you're about 0.0205. About 0.0205. Okay. So we've calculated these things. Now you have to be careful with sampling distributions for sample proportions because we have the standard deviation formula, but you have to verify that it's okay to use that. So and that's what part B is going to be about. Use rule of thumb number 1 to verify that this is okay. So rule of thumb number 1 says that the population has to be greater than 10 times the sample size. So do we believe that the population of people who have cereal for breakfast or some point is greater than 10 times 500 or greater than 5,000. And we're going to assume that, because I'm sure there's more than 5,000 people who eat cereal. And since that's true, then it's okay to use this standard deviation formula. Okay. There's another rule of thumb, though. Now, so we have a standard deviation, we have a mean, and it'd be really nice to be able to start calculating some probabilities. Well, we can't calculate any probabilities unless we have a distribution we know something about. We know a lot about normal distributions. We'd love to have that. And it turns out you can check that. So the distribution of p hat will be approximately normal with mean p and standard deviation p times 1 minus p over n if n times p is greater than or equal to 10 and n times 1 minus p is greater than or equal to 10. This is referred to as rule of thumb number 2. So we need to check both of these and make sure that they hold. So in our case, n is 500. P is 0.7. So we have 500 times 0.7 is greater than or equal to 10. That is true because 500 times 0.7 is 350. So check. We're going to do 500 times 0.3. Well, that's going to be 150. And that's greater than or equal to 10. Check. So yes, this works. We can use the normal approximation for the distribution of p hat. So that means p hat is approximately normally distributed with a mean of 0.7 and a standard deviation of 0.0205. Okay, and that's really nice. So now we can start to answer some probability questions. So part D of this question is going to say the following. Find the probability of obtaining a sample of 500 adults in which 67% or fewer say they would drink the milk that's left over when they're eating cereal. So they really want the probability that p hat is less than or equal to 0.67. Well, I can do that now because I know that the distribution of p hat is normal because we checked our rules of thumb. So this tells us it's the probability that z is less than or equal to 0.67 minus 0.7 over 0.0205. Okay, and we can convert that z-score into a number. It's going to be probability that z is less than or equal to, go to our calculator here, so 0.67 minus 0.7, 0.03 divided by 0.0205, and we get negative 1.46. Negative 1.46. That's on our normal distribution here. We have 0.7 in the middle. And z squared negative 1.46 is down here somewhere. This is z equals negative 1.46. So we get that area. Okay, so I'd like to know what that is. Let's go back to the calculator. We can go to second distributions. By the way, if you had a z-chart, go ahead and use it. You know the z-score. But we'll do normal CDF. And we're going to do some very, very low number, comma, my z-score of negative 1.46, comma, 0, comma, 1. Okay? If you have a z-score, then you're looking at a normal distribution with a mean of 0 and a standard deviation of 1. It's called a standard normal distribution, actually. You hit enter, and we get a probability of about 0.07. So that is our probability here. This area in this corner is 0.07. This equals 0.07. Okay, so that's not very common. It's not as low as, you know, in statistics we have this magic cutoff around 5%. If we were lower than 5%, we start to say, hey, wow, this is really rare. This is close to being rare. So we'll have to see what you think about that. By the way, back on the calculator, you could have also done second distributions, normal CDF. And instead of using the z-score, you could have done some very low negative number, comma, the proportion 0.67, comma, the mean of the proportions 0.7, comma, the standard deviation of the proportions 0.0205. And you hit enter, and you notice you're getting about the same number. Okay, good. So we're able to calculate probabilities and so forth. All right. So the next question might be this. Often, if we're trying to estimate the population parameter, now we suspect in this problem, we're told the population of people, the proportion of population of people who finish the cereal milk is 0.7. I would, you know, you might not really know that in practice. Your goal might be to estimate that. So if you want to estimate the population parameter, it's sometimes desirable to have a very small standard deviation, so you won't have a lot of variability. So part E of this question is going to be this. What sample size would be required to reduce the standard deviation of the sample proportion to 1/2 the value you found previously? So I want a new p hat, and I want it to be half of what it used to be. Okay? So we remember the p hat that we had was 0.0205. So I would like, what I really want is I want sigma of p hat to be half of that. Okay? Or 0.01025 is what I want. So literally, we can just solve for this. What we can do is take our standard deviation formula and figure things out. So I want 0.01025 to equal the square root of p times 1 minus p over n, or in our case, 0.01025 equals the square root of 0.7 times 0.3 over n. I just have to solve this equation. So let's do some algebra. We'll get an answer, and then we'll talk about another way you could have figured this out that you might like better. All right, so I got to get rid of that radical. I'm going to square both sides to do that. So 0.01025 squared equals, now that product, by the way, is 0.21 over n. Let's cross multiply here. So here we go. I'm going to put this over 1 and cross multiply, and we get 0.21 equals 0.01025 squared times n. And then lastly, I have to divide 0.01025 squared on both sides, and then that's going to give me n. All right, let's go type this in the calculator and see what we get. So we get 0.21 divided by, open parenthesis, 0.01025 squared, close parenthesis, enter, and we get Basically about 2,000, 1999. Yeah, really. So n is about 2,000. That would do it. Okay. The smallest number, it looks like we did some rounding here, so that the smallest number is like whatever it may be. All right. So here's what we got. That means we'd have to interview quite a few more people to get our sampling, get our standard deviation to just be half of what it was. So this is often the problem. We're trying to get the sampling distribution's standard deviation to be small. Your n has to get pretty big. Okay, so let's just talk about a second way you could have done this. So let's recall in the beginning of this, we did sigma p hat equals the square root of 0.7 times 0.3 over 500. Now, the problem that we just answered said, hey, we want this probability to be half of what it was. So I really just want to multiply this whole fraction by a half, this whole standard deviation by a half. And actually, that's not so bad. I have 1/2 times this. Now, I'd like to multiply the 1/2 by the things under the radical, but this 1/2 is not under a radical. So I'm going to rewrite it the following way. I'm going to rewrite this as the square root of 1/4. Now, I know that's OK to do because the square root of 1/4 is 1/2. So I really didn't change the problem at all. So now, look what happens. I can put this all underneath one radical. I get 0.7 times 0.3. And that doesn't change because it's getting multiplied by 1. But on the bottom, I have 4 times 500, or 2,000. Well, where have you seen that number before? We just did a whole bunch of algebra to figure that number out. You could see all this complicated stuff we did. What you realize now, it's actually much easier than that. If you want sigma of p hat to go to a half of sigma of p hat, then just take n and multiply it by 4. Remember, we had 500 originally, and then it turned into 2,000. So if you multiply your sample size by 4, your standard deviation will become half of what it used to be. Okay, thanks for watching.